Hello friends, I am Sudhir Vidya. Welcome to Physics Online. We continue where we left last session, that is photoelectric effect part 2, and we will be looking at dual nature of radiation that we already seen, but today we are going to concentrate on dual nature of matter, or what we call it as matter waves, and de Broglie's hypothesis. So the phenomena like interference, diffraction and polarization etc. can be satisfactorily explained only on the basis of wave theory of light. On the other hand, if you look at the phenomena of photoelectric effect, Crompton effect etc. can be explained only in terms of quantum theory of light, or rather by assuming that light is made up of particles or photons or particle nature of light. This shows that light radiation has dual nature. It sometimes behaves like a wave and sometimes as a particle. Now we look at dual nature of matter, and the whole idea was hypothesized by De Broglie. It is spelled as De Broglie, but it's pronounced as De Broglie, and the consequent wave that is associated is called De Broglie waves. So we go back to 1924. Sorry. Yeah, so we go back to 1924. The French physicist Louis Victor de Broglie put forward the bold hypothesis that material particles in motion should display wave-like properties. His reasoning was based on the following two considerations. The two physical quantities which govern all form of physical universe are primarily mass and energy. The Einstein's mass energy equation, E is equal to mc square, shows that there exists a complete equivalence between matter and radiation. There must be mutual symmetry between matter and energy. So if you look at light, which we talk about in terms of energy, and particle we talk in terms of matter, both should behave similarly. Now nature allows symmetry. Since radiation has dual nature, therefore from symmetric consideration, de Broglie predicted that matter must also possess dual nature. Thus particles like electrons, proton, neutron etc. should not only behave like mass, that means it should have mass, momentum, they should also exhibit wave nature, that means they should have wavelength, or they should have a wave property associated with them. The wave associated with material particle in motion, now remember it's material particle in motion, underline the word motion because that's important to us, we will see it as we go along, are called matter waves. Repeating, the wave associated with material particle in motion are called matter waves, or since it is discovered by de Broglie, we call it as de Broglie waves, and their wavelength is called de Broglie wavelength. Now let's consider a photon of an electromagnetic wave of frequency mu. Its energy from Planck's quantum theory is given by E is equal to h mu. Now mark it as 1. Now here h is the Planck's constant. Now considering a photon as a particle of mass m, the energy associated by it is given by Einstein's mass energy relation as E is equal to mc square. So both are E, so we can equate them. So we get h mu will be equal to mc square. Remember that frequency is velocity upon wavelength. So here we substitute the value of frequency mu by c, and doing a little bit of arithmetic, that is you can cancel out one of the c's, we get lambda is equal to h by mc. Interestingly, look at the denominator, mc is mass of the particle, and if it is moving, mass of the photon, and c is the velocity, so it should be equal to the momentum of the photon. So we say that lambda will be equal to h by p, or p is the momentum. Lambda is the wavelength of radiation of frequency mu, and p is equal to mc is the momentum of photon. Now, till now we are only talking about waves. The above equation has been derived for a photon of radiation mu. Now, according to de Broglie, it must be true that material particles like electrons, protons, and neutrons, etc., moving with a velocity v must be associated with a matter wave of wavelength lambda. That means every small particle moving with velocity should have a lambda, and since its momentum is mv, so the lambda associated with that particle should be p upon mv. This is de Broglie's wave equation for material particles. It explains the dual nature of matter as it contains the wave characteristics lambda and the particle characteristic p. Now, from de Broglie's equation, we find that the wavelength of moving particle is inversely proportional to the momentum. So, if the momentum is small, lambda will be big. Now, if v is 0, then lambda becomes infinite. This implies that waves are associated with material particles only when they are in motion. Now, that's an important point to note. If the particle is stationary, or rather it doesn't have velocity, then its momentum is 0, and consequently its wavelength will be infinite. So, we can only talk about wavelength of a particle as long as it is moving. Next point, to be associated with de Broglie wave, a particle need not have charge. That means the charge has no role to play in case of de Broglie waves or matter waves. Any particle which has charge or not, like for instance neutron doesn't have a charge, or you can talk about any body which is neutral, it will still have a wavelength. De Broglie waves cannot be electromagnetic in nature. So, de Broglie waves or matter waves are very different from electromagnetic waves. They are not waves in the conventional sense or the waves till we have studied till now. They are very different because electromagnetic waves are associated with accelerated charge particles. They are only with accelerated charge particles. The dualism of matter, that means the coexistence of matter as a wave and as a particle, is exhibited by lambda is equal to h upon p. Lambda wavelength and p momentum. The de Broglie wavelength is independent of the charge and nature of the particle. So, any particle, the charge doesn't make a difference, and how the particle is, that also doesn't make a difference. Now, the big question is why objects like the one we see around, like for instance you, me, the bus, the car, the football, or even if you take one grain of salt, it doesn't appear like it's a wave, correct? Our idea of wave is something which travels in space, and this looks entirely different. Now, let's examine it. Starting with the equation lambda is equal to h upon m, we see that lambda is inversely proportional to m. So, let's do a little bit of arithmetic and say that we talk about a man who's about 80 kg and is coolly walking at 2 meter per second. His momentum would be 160 kg per meter second. Now, if you look at the lambda associated with the man and you put the values, h is 6.63 into 10 raised to minus 34, very small. Momentum 160, we come out with a term 4.4 into 10 raised to minus 36, and indeed it is very small. So, even if there is a wavelength, it is hardly noticeable, or in other words, we just can't measure it. Okay, it is, but we cannot measure it. Now, let's look at, so de Broglie wavelength of large moving objects is very small, quite beyond measurement. In simple terms, we cannot measure due to its large mass. That is why macroscopic objects, means large objects which we see in our day-to-day life, do not show wave-like properties, or rather simply speaking, do not appear like waves to us. Let's look at subatomic particles. So, lambda is equal to h by p, and we look at a electron whose mass is about 9.1 into 10 raised to minus 31 kg. Let's say it's moving at the same speed as the speed in which the man was walking. So it is 2 into 10 raised to 2 meters per second. So its momentum would work out to 18.2 into 10 raised to minus 31 kg. Key in the values for lambda, and yeah, now see, the lambda is something that could be visualized or measured. It is 3.6 into 10 raised to minus 4 meter. So even though it is small, it's not that small, it is measurable. Okay. On the one hand, subatomic particles like electrons, protons, due to the smallness of their mass, the associated wavelength is significantly measurable. In fact, the wavelength is very small, is significantly measurable of the order of atomic plane spacing in crystal. That means it is somewhere very much close to the distance between atoms or the plane formed by atoms in a crystal. And this point is important when we look at experimental verification of de Broglie's waves, which we could do in the next session. So the last sentence, that is, in fact, wavelength is very small and significantly measurable, and it is almost equal to or in the order of atomic planes. That means the distance between two planes of a crystal. Thanks again. We have come to the end of this session, and the next session, that is the experimental verification of whatever we did in today's class, will be discussed in the next session. Thank you once again for joining, and do take good care of yourselves. Goodbye.